In this video, we're going to cover a couple examples of Coulomb's law. So Coulomb's law gives you the force between particles, charged particles. So if we remember, the force between charged particles is going to be equal to constant K, charge 1, charge 2, R12 hat over R12, that quantity squared, where K is 9 times 10 to the 9th, it's Coulomb's constant, 9 times 10 to the 9th, Newton meters squared per Coulomb squared. R12 is just a unit vector. It's magnitude 1, and it points from 1 to 2, charge 1 to charge 2, and this is the distance between 1 and 2. Now, the important thing to note is that when you're using this, it's always the total distance between 1 and 2. You cannot break distance into components. Repeat, do not break distance into components. Always use the total distance. So let's work a couple examples now. So in this example, you're going to find the force between charge 1 and charge 2. And we're asking you to find the force on Q2, which is this force. So if you draw a picture, you know that this is a positive and positive charges. So since this is a plus, you know it is going to go this direction. So this would be F1 on 2. Okay. And this is in the y hat direction. So with any problem, we always start with Coulomb's law. So F, the force of 1 on 2, equals K Q1 Q2 over R12 squared times R12 hat. So if we break this up, we know that this, from 1 to 2, that just points in the y hat direction. So this is just y hat. This distance right here is the distance between 1 and 2, so that is 1 meter. And those are just the charges. So let's go ahead and plug in these numbers. So we'll get the force of 1 on 2 equals 9 times 10 to the 9th Newton meters squared per Coulomb squared times charge 1, so that's 15 times 10 to the minus 6, micro is times 10 to the minus 6, and always convert to regular coulombs. It just makes the math a whole lot easier, and it makes your constants and everything work. So Q2, which is 20 microcoulombs, which is 20 times 10 to the minus 6 coulombs. Almost made a whoopsie there. Sorry about that. We said that R12 is y hat all over the distance, so this would be 1 meter. That's already in base units squared. So you plug in all of your numbers, and you're going to get that the force between 1 and 2 equals 2.7 newtons in the y hat direction. So key points: figure out what direction it's going. Figure this out by using a picture. All right, go ahead and sketch the force in there. So in this case, our final force is positive in the y hat direction, and we can see that it is positive in the y hat direction. Always convert your units to coulombs, micros 10 to the minus 6, and always convert your distance to meters. So let's look at a little more complex example. So first, let's start with the force. We'll do the easy one first. We're going to say between Q2 and Q3. So opposites attract, so the force here is going to be this way. This would be a force of 2 on 3. And then if you're looking for the force of 1 on 3, it's repel. So force 1 on 3 goes this way. If you're looking for this distance, this would be R 1 and 3 equals, we made each of these 1 meter apart, so this would be, using Pythagorean theorem, 1 meter squared plus 1 meter squared equals square root of 2 meters, which equals 1.41 meter, give or take. Always find your total distance. Then you need to figure out what this angle is. And this angle is 45 degrees. You can get this if you say theta equals tangent to the minus 1 meter, that's y, over 1 meter, your x distance, and this will give you 45 degrees. So let's calculate the force between 2 and 3 first, and then we'll calculate the force between 3 and 4. Not 3 and 4, 1 and 3, because that one's going to have components. So in this case, you now have 3 charges, Q1, Q2, and Q3. And you're going to use this principle of superposition to find the force on Q3. All superposition means is that you are just going to add up all your forces. Now, real quick, remember, first find your magnitude and then break into components. So magnitude, then components. If you do it backwards, you'll get a really weird answer. So looking at this, we start, as usual, Coulomb's law. Let's look at the direction. So if we go from R2 to 3, we see that the distance, or the unit hat vector pointing from 2 to 3, this is going to be just the x hat direction. This distance is 1 meter, and if you plug these in, you will get the force from 2 to 3 equals 9 times 10 to the 9th. Again, you should try this first before letting me go, and then pause, walk your way through it. So Newton meter squared per Coulomb squared times Q2. So this is minus 2 times 10 to the minus 6 coulombs. Q3, so 5 times 10 to the minus 6 coulombs, x hat over the distance, so this would be 1 meter squared. And you will find that the force from 2 on particle 3 is equal to negative 0.09 newtons. And that's your answer. Very important. Pay close attention that you use the distance between them, and always pay attention to the direction. So now let's worry about solving for the force between Q1 and Q3. So when we're looking at this, again, we calculated before the total distance between Q1 and 3 is 1.41 meters. The angle is 45 degrees. So if we start with Coulomb's law, you get the force between 1 and 3 equals K Q1 Q3 R13 hat over R13 squared. Now this R13 hat in this case is at 45 degrees. So when you plug these numbers in, I'll go ahead and do that real quick. We plug in these numbers, Q1, Q3, this angle right here at 45 degrees, and you plug in the numbers, you get your total force is equal to 0.225 newtons at 45 degrees. So we've got the force between 1 and 2, or sorry, not 1 and 2, between 2 and 3. We've got the force between 1 and 3. Now we have to add them. And in order to add them, we have to break this into components. So let's do this on the next slide. So your force between 2 and 3 in the x direction. Well, it only went in the x direction, and it was negative 0.09 newtons. Your force between 2 and 3 in the y direction was just 0. There was no component there. For F13 in the x direction, this would be, let's sketch this over here real quick. Boop, like that. So this is F13. This is F23. And so F13 was your magnitude, so 0.225. You're looking for the adjacent side to this angle. And remember that this angle right here is 45 degrees. 45 degrees. So when you're looking for the adjacent, you use cosine 45 degrees. So your x component winds up being 0.159 newtons. Your F13y equals 0.225 newtons sine, because you want the opposite side, 45 degrees, which is also 0.159 newtons. So now that all that's left is to find your total force. So your total force in the x direction equals this one up here. Add your x components. So you get f of x is equal to minus 0.09 newtons. This is from this charge number 2. Plus 0.159 newtons from the interaction between 1 and 3. Add those together, you get your x component equal to 0.069 newtons. Your y component force. Charge 2 contributes nothing. Charge 1 gives you 0.159 newtons. This is the x hat equals 0.159 newtons in the y hat. And you're almost done. Now we just need to use Pythagorean theorem to get the total magnitude. So your total force is the square root of, so these are the total forces on 3, square root of your x component, in which case, square root of your x component. In this case, your x component was negative 0.069 newtons squared, plus your y component squared, which was 0.159 newtons squared. Calculate this out. You get your magnitude of your force on 3 is equal to 1.173 newtons. Now you need to figure out your angle. So theta equals tangent inverse your y component over your x component, so that's 0.159 over 0.069. Using your calculator, you'll get 66.5 degrees. And you are almost done. You just need to double check to make sure this makes sense. So your y component, 0.159, your x component, 0.069 newtons. Both of those are in newtons. This would be your resultant. And if you look, this angle is indeed close to 66.5, just by my rough sketch. Always draw a rough sketch and always verify. If it doesn't match, you might need to add 180. So the final note is be careful with tangent. If you have any questions, please feel free to stop by my office, ask me in class, ask me in the hall. As long as you're asking questions when you have them, that's the important thing. Well, I hope this helps, and I will see you in class.